Okay, we have already introduced the idea of an integral. F of x is always, the function is written there. That should be in parentheses. Dx tells us that we're working relative to the x-axis. And then we worked on A to B. All right, so who could tell me what that means? Okay, and what will that give you? Okay, so the meaning of this is the area, and you're talking about a strategy, okay, a way of adding them all up. Okay, so this is exactly equal to the area between A and B, okay, closed interval. And also, not just between A and B side to side, that's the side to side of it, but what's it between top to bottom? Okay, the area between A to B side to side and between f of x and the x-axis. All right, that is the meaning of that symbol. Now let's talk about the methods. Okay, that is the meaning. Now let's talk about the methods. Okay, Lucas, you were sort of alluding to it, right? Well, the first method we learned was adding up shapes. Okay? So one way is to add up geometric shapes. There are different methods within that. Sometimes it's just straight a geometric shape, like a semicircle on top of a rectangle. Sometimes it's a bunch of rectangles added together. Sometimes it's a bunch of trapezoids added together. Sometimes it's a bunch of paraboloids, that's Simpson's method, added together. But it's adding up of a whole bunch of geometric shapes. Okay, another method we learned to evaluate that. We learned that yesterday. Yep. And then one other one. Just with your calculator. Math 9, right? Okay, Math 9 on your calculator. All right, so number 2, we learned Math 9. Okay, so when would you use Math 9 as opposed to the second or the first method? Okay, well, yeah, clearly when you can use your calculator, but also when the shape is not geometric. Okay, if it's not a geometric shape, you got to have a different way. Okay, so what if the shape is not geometric and you don't have your calculator? Right, that's where Adrian's getting to. We need a third method to be able to evaluate that, and that's the antiderivative. And so that is method number 3. So they just lead up to each other. We're just building towards this pinnacle moment here where we are going to figure out how the antiderivative is connected to the integral. So if you can do geometry, it's always the easiest way. Geometry is always easiest because it takes the least amount of work because it's like 1/2 base times height or whatever. Geometry is always easiest. If you have your calculator, that is the next easiest way because your calculator can figure it out for you. But more often than not, you'll be asked to do it without your calculator, and it will not be geometric, and so then you need the antiderivative. So here is the big takeaway thing for today. A to B of parentheses f of x parentheses dx is exactly equal to the capital F of x, which always has a plus c on the bottom, and then we show that it has boundaries. We put brackets now, and on the second bracket you put a on the bottom and b on the top. So you're converting from an f of x to a capital F of x. and you're moving your bounds to the bracket. It's just a notation, a way of showing the person who's reading your work that you've now done the antiderivative. And then what do you do with the bounds? You start with the larger bound, and you're going to plug that in. And so f of b plus c would be a value where you would plug b into that equation. That's called the upper bound or the larger bound. You'll also plug in the lower bound, f of a plus c, and that will give you another value. And you are going to subtract those two values. And the result of that would be the exact area value that you want. Okay, there is no approximation. There is no, is it going to overestimate or underestimate? It is exactly spot on, exactly the area under that curve, between that curve and the x-axis, bounded side to side from A to B. All right, so this is like big, huge takeaway thing today. All right, this is called the fundamental theorem of calculus. There are some universities that like to stress the "the" in front of them and say "the Ohio State University" or "the," because there's more than one and they want to make sure everybody knows that they are the premier one. So this is the fundamental theorem of calculus. That you can take any function, that's continuous, any continuous function between two bounds A to B, and you can find the exact to the decimal point value of the area using the antiderivative. And now it's just, okay, we're just going to practice this. All right, so let me show you how we would practice this. You would be given the following question. The integral from -1 to 1 of parentheses 2x to the 4th minus 4x squared plus 2 relative to the x-axis. So it's always good to just have a visual of what you're looking at. This is a quartic function. Okay, this particular quartic function looks like a W. It looks like this. And then like this. And it has perfect, beautiful symmetry from -1 to 1. And so we are looking for the amount of area, the exact amount of area bounded between -1 to 1 between the function and the x-axis. So that's what we'll be finding. All right, so we start with bracket and we find the antiderivative of each piece. So 2x to the 4th becomes 2x to the 5th divided by the new power of 5. 4x to the 2nd becomes 4x to the 3rd divided by the new power of 3. And 2 as a constant becomes 2x. Plus the constant c evaluated on the bounds from -1 to 1. And so you always plug in your upper bound first, and you work through the math. So plugging in 1, I'm going to get 2/5 minus 4/3 plus 2 plus c. Plugging in -1, I will get -2/5 plus 4/3 minus 2 plus c. And between those two things is subtraction. And so you'd want to distribute the subtraction to the second term. So we'll have 2/5 minus 4/3 plus 2 plus c, and then I'm going to distribute this negative all the way through. that would give me plus 2/5 minus 4/3 plus 2 minus c. Now I want to combine like fractions if possible. So I have 2/5 and another 2/5, so that's 4/5. I've got negative 4/3 and another negative 4/3, that's negative 8/3. I've got plus 2 and plus 2, that's plus 4. And then what about the last, the constants? Yeah, they cancel each other out because one is plus c and one is minus c. So I end up with 4/5 minus 8/3 plus 4. I want a common denominator of 15 to help me out with that, so that'll be 12/15 minus 40/15 plus 60/15. So 12 minus 40 plus 60 is 32/15, which represents the exact area bounded under that quartic curve, starting at -1 and ending at +1. Yeah?
Those things will always cancel each other out.
They will. Just have to write it. Okay, now, some tricks of the trade that you might start to use. If you notice, this graph is perfectly symmetric. If you notice the graph is symmetric, you can use that to your advantage. What you could also do is you could only find half the area. What would your bounds be then? 0 to 1. What do you think you'll get as your answer? Well, we just did the whole thing, so what do you think you would get as your answer? You'd get 16/5. But then to answer the question, you need to double it. But a lot of times, using 0 as a bound is easy because when you plug 0 in, it like wipes out a whole bunch of the problems. So sometimes you can be a little smart about it, and if you notice symmetry, then use that to your advantage. Change the bounds, just remember to double your answer when you get to the end. All right, let's try another one. All right, let's look from 4 to 7 of the function 1 over x minus 2 dx. Now 1 over x minus 2 is a hyperbola. It is not a continuous function. I just need to check where my bounds are. As long as my bounds are on a part that is continuous, it's fine. All right, 1 over x minus 2 means it's a hyperbola shifted 2 to the right, so I have a asymptote at 2. And my hyperbola looks like this. Now my boundaries are both on the same side of the asymptote, so that's fine. Okay, what if my boundary had been -4 to 7? Okay, that would have been a problem because -4 to 7 would have crossed over an asymptote, and that's actually exactly what we're doing in BC right now, is figuring out how to handle area when you have an asymptote in the middle. Is that possible? And it is in some cases. Okay. But we are going to do from 4 to 7. So 4 would be about right here. 7 would be here. And so I am looking for this non-geometric region from 4 to 7. Okay, this is a situation where natural log is the antiderivative. And so in a bracket, the natural log of the absolute value of x minus 2 plus the constant c going from 4 to 7. So then in parentheses, the natural log of the upper bound of 7 minus 2 plus c minus the natural log of the lower bound of 4 minus 2, also plus c. And we'll distribute our negative. Now 7 minus 2 is 5, which is a positive number, so I don't need the absolute values anymore. So the natural log of 5 plus c minus the natural log of 2 minus c. And the c's, again, we see that they cancel out. And so I'm left with the natural log of 5 minus the natural log of 2, which when you do the properties of natural logs, that's the fraction, the natural log of the fraction 5/2. And that represents the exact area to the infinite decimal. This is an irrational number, but it's still the exact representation of the amount of area between 4 and 7. Okay, I'd like to do one more with you. From -2 to 2 of the cubic function x plus 1 cubed relative to the x-axis. When you have a quantity cubed like that, you're going to have to do some algebra before you do the antiderivative. Okay? And so prior to the antiderivative, you would need to expand that to be x cubed plus 3x squared plus 3x plus 1. Okay, that is x plus 1 times x plus 1 times x plus 1, and that's the quantity that you end up with. Because you need to take the antiderivative of each term individually as you go. And so there are opportunities for you to take to do algebra before calculus, rather than calculus before algebra. Then you would take the antiderivative of each one. So the antiderivative of x to the third is x to the fourth over 4. The antiderivative of 3x to the second is 3x to the third divided by the new power, which will eventually reduce itself. And then 3x to the second divided by the new power of 2. Antiderivative of 1 is x plus the constant c from -2 to 2. This function did not have symmetry because it was a cubic function moved 1 to the left. Okay, if I'd looked at my graph on here is a cubic function that goes like this. But my bounds take me from -2 to 2. So, but there is still a trick I can employ with this. So I'm looking at this area right here, from starting at -2 up to this area, and then including all the way up to here. Now, although this is not completely symmetric, I can still use some smarts about adjusting my bounds. Because this section right here is perfectly symmetric with itself. And the first little piece of area is considered negative. And the second little piece of area is considered positive. And so those two things are going to do what to each other? They're going to cancel each other out. And that's going to be 0. And so I could, knowing that that's going to be 0 area, I could adjust my bounds and know that I could simply go from 0 to 2 and come up with the correct answer, because the area from -2 to 0 is not going to impact the final answer at all, because it would completely cancel itself out. And so for me, I guess it would be, I'd prefer to plug in 2 and 0 as my bounds, because when I know that when I plug in 0, all of those polynomial pieces will drop away. Okay? So use geometry and symmetry to your advantage to maybe help you out in saving you some work. Be careful though about trig, because if you try and plug 0 into trig, it's not always just simply 0. Don't make that assumption, oh, I'm plugging 0 in, it's just going to all wipe away. In polynomials, yes. But in a trig function, 0 into cosine is not 0. 0 into cotangent is not 0. 0 into secant is not 0. So be careful when you're plugging in 0 into a trig function. Don't make a poor assumption.